Okay, let's start. So, what is CERN? CERN essentially is a combination of countries, of currently 21 countries. CERN stands for Conseil Européen pour la Recherche Nucléaire, which is the European Council for Nuclear Research. Why we are called nuclear, we're coming within the talk at some point to this. And CERN essentially has three main missions: innovation, education, and research. And all of this together we call uniting people. So, the idea of CERN in the very beginning of the fathers of CERN was to push back the frontiers of knowledge. For example, to find out about the secrets of the Big Bang, which was at the time that CERN was started, which means just after Second World War, was something which was a relatively new concept. And the question was, what was the matter like at this time? So the question is, where do we come from, where do we go to, and what are we made of? Yeah, that's a quest that started about 2,500 years ago with Descartes, who said that particles have smallest ingredients, and we are going to come back to this a bit later. So, in 1949, there was a group of people who have established that one should do civil research on nuclear physics. You know, after Second World War, nuclear physics was a purely military field, and nobody really thought you can do this in a civil way. So those people put themselves together, wrote to their governments, and managed to get this done. We're going to go far deeper into history when we go to visit the simpler cyclotron this afternoon, because there you'll see a movie about the history, how CERN began, how it evolved until 2012 essentially, when we produced the movie. And also you learn a bit more about the countries which are involved at which time of the lifetime of CERN. So one of the first missions is research, so push back the frontiers of knowledge, but also develop new technologies for the accelerators and the detectors we need in order to probe nuclear, to probe particle physics. And also, but that came a bit later, was information technology, the web, the grid, but also all the spin-offs that we have from this. So currently at CERN there is a few mainstreams, one can say. One of them is the LHC, of which you all have heard of which you all will hear a lot during this week. But there is also many different things. There is information technology, for example, in terms of the grid that we need to cope with the data from experiments like the 7 LHC experiments, but also tools for communication like the web, but also spin-offs like medical imaging and medical therapy. But one of the main missions of CERN that we put quite highly is training. Training and education. One part of the education program is you. It's part of the education program, but also part of kind of the recruitment program, because something is definitely missing at CERN, and this is human resources. CERN is well known with all physicists in the world, but if you would know that there are only 71 posts at CERN to do physics research, then you start to think, why? CERN is a research laboratory? No, CERN itself doesn't do research. CERN itself doesn't do fundamental research. We do research in order to have the infrastructure so that others can come and do the research. So if you look at the employment profile at CERN, you mostly find engineers and technicians, where under engineers I also put applied physicists, but not particle physicists. As I said, there are 71 posts out of 2,430, more or less. Yeah? So essentially it's a place for engineers and technicians. So this is something we are doing here. We are training scientists, we are training engineers, and in order to get them to CERN, I think it's also quite important that at schools people know what we're doing here. And of course, this all comes together. We are currently crossing the 100 countries mark in terms of institutes working here. So we are uniting people from different countries and different cultures. So one thing you will see when you pass your hostel here on the CERN site, I think you are in building 39, or where are you? Some of you in building 41, yes. Maybe. So there is between 39 and 41, there is one building which is a bit lower. There you will find a plaque which says that was the first Israeli-Palestinian student party happening here. And this is something which happened during our summer student programs in, I think, in 2006. So this is something we really promote, is uniting people from different countries and cultures. Now, CERN was funded finally in '54. This is why you saw also the CERN 60 logo on my first slide. At the time it was 12 European states. All of them are still or again member of CERN, except one, which is Yugoslavia, which doesn't exist in its form when it was member at the time anymore. But we currently have Serbia as a country in accession to membership. We have Croatia, which wants to become a member, and Slovenia. And I think next week or the week after, we have a Montenegrin teachers program coming. So there is also a lot of people interested in what we are doing. Currently we have 21 member states. CERN is a European laboratory, and if you look at the list of member states, there is maybe one country where you ask the question, is this European? This is Israel. So let me ask the question a bit differently. What's the highest mountain of Europe?
Mont Blanc.
Mont Blanc. You learned that all in school. I did also, but it's wrong. Because 1756, the British, who thought they ruled the world at the time, did some survey of the world. And for them, Europe finishes at the Ural Mountains and goes down through the Caucasus and so on. And it finishes essentially at the Sinai. Yeah? So, for example, Israel belongs to Europe. And the definition we take is members of the Council of Europe. Or for you, or maybe rather your pupils, those people, those countries who sing in the, how is it called nowadays, European Song Contest. All of those countries are the members of Eurovision or the Council of Europe, and they can be essentially members of CERN. So it's a larger definition of Europe than the EU definition or whatever older definition there might be. So Israel will be or is a full member. The same applies to Romania and Serbia, and then there are several applicant states. And you also see here associate membership. You see Brazil definitely does not into the definition of Europe. Pakistan, to my understanding, also not. And all those countries can now be associate members. Since 2011, we can have associate members at CERN. Associate member states have a few, how shall I say this, a few incentives less than full members, but they also have less dues. So what do you think does it mean to be a member state of CERN? Any idea?
Maybe to use some, maybe scientists, they can visit CERN and participate in program different.
Finance.
In principle, so finance is one thing. Mm-hmm. Your idea is logical, but it's not the right one, because everybody can come to CERN. Everybody can come to CERN. We now have institutes. I think beginning of January we crossed the 100 mark, because we are now at 103 countries, institutes from 103 countries who do research here at CERN. No, in principle everybody can come here, but only those institutes that come here from member states don't have to pay for the infrastructure, because this is already covered. Institutes coming from other states, when they want to do research here, have to contribute, for example, to the energy cost. Yeah. Not yet really. There is some how shall I say this, rent on apartments, like on the offices, like on an apartment. But maybe at some point we'll get there. So financing CERN. CERN has a budget of about 1 billion Swiss francs, and this is. What do you think? Is this a high budget or a low budget?
Low.
Low? Why?
Oh.
I mean, for your pocket and for mine, it's probably a high budget.
Yes.
But in principle, that is comparable to a small university of 20,000, 25,000 students. They have more or less the same budget. If you look at universities like Zurich, for example, they have a budget of, Zurich has 7.3 billion, with all the money coming from the sides. So it's a relatively low budget, and it's distributed among the member states, among those 21, by their net national product. So you add up the net national products of all those countries, then you know what 100% is, and you know the fractions of the countries. So currently I can tell you, for example, that Germany pays 19.3%, and Bulgaria pays 0.5, but maybe 0.6% of the budget. Yeah. So this is how budget is distributed. So this is one due. But are there also positive things, apart from the fact that institutes don't have to pay for power? Yes, there is one positive thing, that member states can send staff to CERN. So people who are paid to work here at CERN. International staff, and especially international staff with unlimited contracts, they can only come from member states, with 3 exceptions over the years. The associate members can also send staff, but not for indefinite term. They can only send them for up to 5 years, or in the future maybe another contract duration, but only for limited time. And one thing that all of the countries like the most is that we have to essentially get the money back to those countries in terms of orders. So we have to order material from the member states, essentially, and only if we cannot get the material in a member state, we are allowed to buy it elsewhere. And we have to do it according to the percentage. So theoretically, we would have to order 1/5 of our goods in Germany, but that's impossible. This is possible when you build something like the LHC, where you can say, okay, you can build steel tubes, you can build aluminium tubes, and so on, and get them. But during a running period, like we are now, you buy mainly services. And there, you cannot really redistribute it. So this is a game which you have to play, but in principle, the countries get a lot of money back from CERN. About half of the money goes back into the countries. The other half we pay to staff, but also to visiting scientists, or we pay in France or Switzerland, our host countries. Okay, so apart from the member states and the applicants, there are also some observers to the council, which are the 5 states in the first row of observers who contributed more than 50 million, especially to the LHC. They were allowed to be observers, but also the European Commission and UNESCO are observers to the Council. Now, about 2,300 staff. You always hear different numbers between 2,500 and 2,200 more or less. The question is always, what is the number of posts and what is the number of heads? Because you, of course, can have, we have, I think, at the moment 2,210 posts, but of course there are 50% posts in there. So you have sometimes 2 people filling 1. We have something like 1,600 persons, other paid personnel. These are, for example, fellows, doctoral students, all of them who get money from us. Theoretically, the teachers in summer who come for the 3-week program as they also get something for their stay, because they are paid for their stay, essentially. They are also on the payroll there. And we have here, it's still written 10,500. We crossed the 11,000 users mark sometime last year. So this is those people coming from institutes from all over the world who come here and do research. They are not all here 100%. They have fractions of 5 to 100% here. Some of them are based here for their institute. Some of them only come for meetings and work from their institutes. But in total, we have something like 10 to 12,000 people on site every day. So this is the, say, 2,400 staff to make it easier, plus the 1,600 paid. We are already at 4,000. We have about 4,000 people from companies on site every day, including the guards, the cleaners, and so on, plus something like between 2,000 and 4,000 of those users on site every day, plus 100,000 visitors every year. So this is what we have normally on site. Now it's getting more and more global, as you can see. This is the map and the numbers from about a year ago, from January 2014. I don't have more current numbers now. So here you see in blue the member states. There are a few states which are wrongly colored. But you see the member states, you see the observer states in green, the candidates and the associates, they are extremely small in here. And you see the other states. But this is the map of the institutes. So if Lithuanian, for example, you will meet, I think, at least 3 Lithuanian engineers and scientists here at CERN. They are not marked as Lithuanians on this map because they are working for, I think, MIT. So they are marked as American here because this is the nationality of the institute. If we would take the nationality of the people, then essentially all of Asia would be colored and half of Africa would be colored. So this is the institutes. Yeah, that's always a bit tricky to see that, because then you say, but from my country there are people, but we are not marked. So this is the institute nationality. And as you see, 98 nationalities. And one thing that especially our Director General likes to point out is the age distribution. So this is the age distribution only of the users of CERN. Only the users. We have some other categories of personnel, like honorary members, that are more in this part of the screen. Yeah. So, but what is quite interesting is it peaks at 26. So most of the people who use CERN are relatively young people, and this is mainly doctorate students. We had in 2013 and 2014, we had over the whole time always about 3,500 doctoral students who did their thesis at Atlas and CMS only, plus the others. So this is the age distribution of it. Here there is a point at 85. This person just turned, this is 5 years old, so the person turned 90, is in principle still on this, but he's not the oldest one that we have in our database. We have, you will see in the movie that you will see at Synchrocyclotron this afternoon, you will see a couple who is here essentially since the extremely beginning. So they started their first experiments here at CERN in 57, but they were here already before, and they are still here. They are here every day. I had, for the last 8 years, I had an office essentially close to them, and every day, including Sundays, they came here and worked. Good. So how is CERN organized? Relatively easy. We have a CERN Council. All member states are represented there. The current president and also the first female president of CERN Council is Agnieszka Zalewska from Poland. And she was just renewed as president of council for another year. Council takes all the big decisions. They meet 4 times a year, usually for 2 days. And then they have two big subcommittees. One of them is the Finance Committee, meets 5 times a year, also in the same weeks as Council in normal circumstances. Also a woman as a chairperson currently, Charlotte Jameson from the UK. Also there are all states represented, but the terms of voting are completely different. While in Council, it's the majority of member states usually, where a lot of things need to be decided in consensus. In Finance Committee, you have always a double majority. You have a majority of the countries and a majority of the budget. Because of the 21 member states, 5 of those together bring 80% of the budget. Yeah, if you do this by net national product, you find 5 that in total give 80%. So if you would only vote on budget terms, those 5 countries could steer the 21. If you would only vote on number of countries, 11 countries that in total do not represent more than 10% of the budget could steer what is done with the budget that the others give. So there is also a double majority, which gives quite a good balance. And as far as I understand, we are the only international organization that looks at all those balances. Then we have a scientific policy committee, which is there to look that CERN is doing no military research, that CERN is staying within its mandate with the research, and that also looks into big programs. So they won't decide whether a small experiment of 100 persons is possible or not. They look, will there be an LHC, and what is the physics program at it. 16 individual members, there for 3 years, 1/3 we exchange every year. And the chairperson is currently Tatsuya Nakada. Sounds Japanese, he is also Japanese origin, but he is Swiss in the meantime. So he is counting for Switzerland here. I think he's in Switzerland for at least the 20 years I know him, at least he's here. Good. Now, CERN the laboratory. CERN the laboratory means 19 different places in the Pays de Gex, which is the region between the French Jura and Lake Geneva. Here, we are currently on the site of Lab 1. We are essentially the main building. We are here, below this tree. And this site is the only site which is on the 2 host countries, on the Swiss and the French territory. The border essentially goes through here and then over there. So on site of Lab 1, this is about 800 meters. This is about 1.8 kilometers. There, everywhere you can pay with Swiss francs. And this border doesn't mean that there is a border check, and there also was none before Schengen. But it means that even though the whole sites are extraterritorial, there is different types of law governing those. So for example, employment law, on the Swiss territory, 42 hours a week, on the French 135. Not for us. CERN employees have a 40 hours week. But all the people from the companies coming here need to follow their national work law. So this means it depends if I have a technician who changes a light bulb in this building or in this building. The question is, can he still do that? So the last 7 hours he can only work in Switzerland. No, that's unfortunately not the case, because they have to definitely stay on their territory, except they are internationalized. There is a few other specialities. Here is a small tunnel that tunnels essentially the border. And this we can use in order to transport material. It's not a quantum effect. You can really drive through with a lorry through this. And this is something the host states accorded to us end of the 60s, which is there in order to transport material so that you don't have to go through customs all the time. So if you are a physicist and you have your office here, like I had my first 10 years at CERN, and you have an experiment more or less over there, and you just need to go there to measure something, and you have an oscilloscope for $500,000 in your trunk. You don't want to go through customs, pay your customs dues, pay them back when you come back an hour later. So in order to do this, you can use the tunnel, for example. And there is another thing which is quite special. This is this building over here. This is restaurant number 2, where you can also have your lunch, or only your lunch. They don't have breakfast nor dinner. This restaurant, as I said, the border is here. So this would have been a restaurant on French soil, where you can get, with Swiss currency, Swiss produce, you can eat it, and this of course is, according to international law, impossible. So they changed the border here. The border was somewhere. So the border was somewhere here. You still see. I don't know. Did they re-put the stone after they built Linux?
I'm not so sure. Did they really change the border, or was
yeah, they really changed it. And now you still have the stone somewhere.
No, the stone is still there. If you want to see it.
The stone is still there. Okay. So they changed it, and as far as I understood, this is the only non-military exchange of land between Switzerland and France, at least after the Middle Ages. Good. As I said, 19 sites, 1 split, 3 more in Switzerland, and 15 entirely in France. Now, how is the day-to-day work organized? We have a Director General, who is currently German, Rolf Heuer, who is here in his 7th year. Normally, a Director General has a mandate of 5 years. There was only 1 before who was extended. And this Director General, on his highest level up there, you have all the things that an international organization needs. And then you have the 3 sectors that make up CERN. Then you have a sector for administration and infrastructure, always with a director, these sectors. And in these sectors you have departments. So administration and infrastructure, you need human resources, you need finance and procurement, and general services. They are, for example, responsible that the light in here works, that we are not freezing to death, and things like this. These down here we call departments, and in there we then have the staff of CERN. On the right-hand side you have the part that is responsible for our technical infrastructure with, if you excuse me, Nick, because I'm going to simplify this a lot. Technology is thinking about new accelerators. They are building it with engineering, and they are running it together with beams, more or less. There is by far more subtleties to it, but I think we will learn. We will learn about accelerators tomorrow.
No,
good.
Wednesday.
I always mismatch. I always want to push it. So, and in the middle you have the sector Research and Scientific Computing with 2 departments, the IT department. I think the most known spin-off of IT at the time, it was called DD, Data Division, is the World Wide Web, which was thought of 26 years ago now. So last year we celebrated 25 years of the web. In order to make the communication possible between the always growing collaborations. Because before we started LAB, the accelerator, which was in this 27-kilometer tunnel before we started the LHC, collaborations exceeded 100 participants. So that was the first time then. And people thought, how can you communicate? And this is how the web started. And then you have the biggest department at CERN, the physics department, with about 500 staff of the 2,200. And also there you find all users. So that's the day-to-day organization of the laboratory. Now let's go a bit more to scientific challenges. So one of the big challenges we have is to understand the universe, and in this case the very first moments of it. So the idea is to go back in time about 13.8 billion years, plus minus 70 million, that we are now sure. So this means from a scale of a point that we had at the Big Bang to the scale of 10 to the 28 centimeters. One thing you can do is you can look into this with light. So you can look at stars, for example, that were built at the time. But the problem is, somewhere here, about 380,000 years after the Big Bang, only then universe became transparent. Before, you couldn't get light out. So you cannot look deeper with telescopes, for example, into the universe than to this border. Now, you can see this as a matter of time, but also as a matter of size. So we are more or less on the level of 1 meter or 10 to the 2 centimeters. If you want to look into the universe, you go to radii of about 10 to the 28 centimeters, and there you need telescopes, either light telescopes, radio telescopes, large arrays, or also one smallish telescope on the ISS, where CERN is also involved. You will see, I think, on Thursday morning, the ground control station of this experiment. Or you can try and look at sizes which are extremely small. For this, you don't need a large telescope, now you need a large microscope. And the largest microscope that exists on Earth is the microscope. And here we are more or less at sizes that we can see, that can have a resolution for of about 10 to the minus 16 centimeters. So that is the smallest we can see. And we know, for example, that an electron is point-like in this structure. And there we come to our research history. So here we are with Demokrit, who said there are smallest ingredients. He called them atomos at the time. And essentially until the end of the Romans, people were researching on this, but you never got smaller than essentially sandcorns. Then about 2,000 years, nobody really looked into it. And it started with Rutherford again, when he found out that gold foil is not completely robust, that, that we knew a bit more. So we went to molecules, what we call atoms today, to how atoms look like, i.e. a nucleus and an orbital of electrons around. Then we looked a bit deeper into the nucleus and found protons and neutrons, and then we looked a bit deeper into it and found that there is a such structure to protons and neutrons. Now, at which time was CERN created? What do you think? Where are we? We were not here. Then we would celebrate 2,500 and not 60 years. And we are not here, because then we would celebrate about 40 years. So the quark model was published in '64. So we were more or less here when we looked into protons and neutrons. So we're there when we talked about nuclei. So particles in the nucleus. And this is where our name comes from. This is why we are the European Council for Nuclear Research. Yeah. Nowadays, we don't want to keep this title on the one hand, because nuclear nowadays is something where people are a bit reluctant to work on. Even though we don't have a reactor, we also essentially never had one, at least nothing to produce energy with. On the other hand, CERN is a brand. If you ask somebody in the world what CERN is, you will get quite a lot of return. If we would call it ourselves now European Laboratory for Particle Physics, which is essentially what we are doing, then people wouldn't really know where this is. So we stay with the term, and from time to time we have to fight against things like Michelin. If you buy the newest Michelin map, you will find the sign of a nuclear power plant where CERN is, because they just heard the term nuclear and put a power plant there. I don't think we have one closer than 60, 70 kilometers. Pierlat must be the next one.
Sascha, you can also say that nuclear is what they do in hospitals today. Globally, this nuclear medicine, because of
we'll come to this.
toxic treatment, radiation therapy, that's nuclear. We don't do that.
We'll come to medicine in a second. Actually, you will get on Friday a quite passionate talk about nuclear, about medicine in general, and also about what we are doing. Good. So we are trying to study the physics laws essentially from the very beginning. And if you put all of this together, unfortunately, I also only have this in German. I've never had the time to translate it completely. So if you put all the knowledge we have about particles together, we'll come to the so-called standard model of particle physics, which goes back to those in total 12 matter particles and some more that transmit forces. But we're going to go into more detail just after my talk. You will have the first of 4 lectures about particle physics and cosmology. So we are going to go far deeper into this soon. And if you look at this model, the heaviest particle, the top quark, was only experimentally shown in 1995. So it's relatively new that this is half complete, because there is one more particle, one that is transmitting essentially something, force or a field, better to say, which was only published 3 years ago, namely in 2012, where it is already something to be on the cover of Physics Letters, which is a pure physics publication. There, that was the day, that was a month, I think, later. It was the issue of June, but which came out only in August, with the publication of the Higgs boson, which was discovered, which was finally found by 2 experiments. But what made it to me quite impressive was we made a leap onto the cover of The Economist. Yeah. A leap for science, finding the Higgs boson, meaning that 38 years after the theory was published, 48 years after the theory was published, finally there was the possibility to really find it, after a worldwide effort to find this particle. So I'm just going through the 2 event displays because Rolf is going to explain those to you. The Physics Nobel Prize went to Peter Higgs, the person who gave the name to the particle, and François Engler, because essentially there were 2 teams, one single physicist and a team of physicists who published the theory at the same time in 1964 without knowing each other before. And in fact, this picture that you see here shows not actually the very first encounter of the 2, because that was a few hours earlier, but that was essentially the first day the 2 met in person, 48 years after working on the same subject and publishing the same theory. So the particle is named after Higgs because he was the only one who in his paper said, if this Higgs field exists, there must be a particle representing the field, a condensation of the field. And the others just were talking about the mechanism. And CERN was involved in there. In the laudatio of the Nobel Prize, they put in that it was recently confirmed by the Atlas and CMS experiments. So kind of this was also something that CERN helped a lot to get. And this makes then the standard model complete, essentially. Good. So, what are we doing here at CERN? This is another aerial of CERN. Up there you see the Mont Blanc, the highest mountain of Western Europe, and we are looking down from the Jura, essentially here. This here is now from the other side the characteristic triangle of CERN Lab 1. On the side of CERN Lab 1 there is one accelerator which is now 55 years old, but still heavily used. That's the proton synchrotron. It was inaugurated on the 1st of December 59 and is now mainly used as a first step, as a third step in our accelerator chain in order to get the protons into the LHC. Then we have this, let me call it medium-sized accelerator, the SPS, 7 kilometers circumference, and mainly in France. And then we have the LHC, or the former lab tunnel. When I came here it was the lab tunnel, which is now our flagship accelerator, and where we accelerate protons to this year to 6.5 tera-electron volts, 6.5 million times their rest mass, and get them into collision in 7 experiments in total. Now, if you look at this in the view of our press office, it looks like this. There are some kinks in the beamlines that, of course, don't exist in beamlines, but that would be a nice thing if you could have real kinks in beamlines. You could spare a lot of space if you could do that. So, what you will visit this afternoon is the ESSI, which is the old work anymore. You will have a look at Lear. And over the week, you will also see the AD, and you will go into an experimental cavern of the LHC. You will not go into the LHC tunnel. That is not possible anymore. So if you follow the road of a proton, which you will also see in the movie this afternoon, we essentially nowadays start with LINAC 2, go through the booster into the PS. There we go to 24 times the rest mass of the proton, go into the SPS, all in one direction still, and come to 450 times the rest mass, and then we go into 2 directions and get the particles in the LHC where they are then accelerated. So this is the current view of our accelerators, and you will hear in many of the talks different details about those and the experiments. If you look at the LHC or our bigger accelerators in a cutaway view, you see that we have here the landscape. We have the LHC between about 50 meters deep here and about 175 meters, but there is no experiment here. So the LHC is not lying like this in the landscape. It's mainly the terrain that goes up. The LHC has a tilt of something like 1.5 degrees, and you have currently 4 big interaction regions where we cross the beams, and there we have the 4 big experiments which I show you just briefly here. Atlas, which is just across the road here, it's the biggest experiment, 44 meters long, 24 meters in diameter, but only 7,000 tons heavy, so as heavy as the Eiffel Tower. And essentially, if you would put it into plastic, I was told, it would float. I don't think we'll ever try this, but maybe in 2036, we will see. Maybe somebody's going to give me a retirement present and really float it. If in 2036 we really stop the program.
If we stop it.
If we stop it. When I came to CERN, the lab was due to finish, and then it was extended by 6 years. So now the CMS detector is on the other side of the ring, and this is essentially the one that you will see live. You will go into the cavern and see the detector directly, I think also on Thursday, sorry. And CMS essentially is 1/8 of the size of Atlas, but it's twice as heavy, 14,500 tons, definitely doesn't float. And these two experiments are looking at the complete physics we can do at this energy range. Why do we have two? That's quite easily explained, because you always need to compare results and also to check results. And nobody will build an LHC in the nearest future or ever again in order to check the results that we have there. So you need at least two all-purpose experiments at such an accelerator. Then we have an experiment which is called LHCb, about the size of CMS all in total, but not as full with instrumentation. And essentially this is one of the experiments, it's the LHC experiment where we don't have the interaction point in the center, we have it at one edge. So the idea is here to look only into a cone, so only a part of the results of the collisions we create. And LHCb has as main goal, which they already essentially fulfilled, to find out about CP violation with B mesons, with B quarks. CP violation is one of the reasons why we are here and made out of matter, and where the antimatter might have gone just after the Big Bang. But Rolf is going to go into more details there. And then there is Alice. Alice essentially has a double meaning, Alice in Wonderland. This is what they really think they are doing. And a large ion collider experiment is essentially what the name means. So in the LHC, somewhere between 4 and 8 weeks a year, essentially we collide not protons, but lead cores. So cores of lead atoms, 82 times positively charged cores. And Alice has a very high resolution detector in the center in order to look at all the tracks coming from all the debris coming from this collision. And their first goal was to look into quark-gluon plasma, but they are also working when we collide protons, and they are also looking into different other types of, there we can just say nuclear physics ideas. Now this is a very old scheme, but I think it's still more or less correct, which essentially says the end of our long shutdown 1, which was the first long shutdown in the lifetime of the LHC. So, which essentially tells you we are more or less here. So the machine checkout has started, and at some point, I guess May, June, we will have physics. I don't know, we have to have a delay again. Good. This is a diplomatic question, not going to go deeper into it. What we can see, this is even older, but I think still correct, is the schedule beyond LS1, beyond this long shutdown 1, which is not even really on this plan anymore. And here you see we have a physics program until 2035 officially, but as you can see, this run is a bit short compared to the others, so there are some ideas for the time after. I will definitely finish seeing it more or less here, probably. And so what you can see, what is maybe interesting for you at your schools is, for you it's more interesting to see the red parts, because then you can come and go and visit in the underground. For us, for the physicists, counting myself still as an experimental physicist, the green and the beginning of the red is the interesting part. And for the accelerator people, it's always mainly interesting in this part. Does it start again? This is the perception of an experimental physicist. Good. But what are we also doing? We are also doing innovation. So we are trying to interface fundamental science and key technological developments. So many things you use nowadays are spin-offs of the research that is done here on accelerators and detectors. So spin-offs are essentially things like, for example, the multi-wire proportional chamber, that maybe you even teach in school. I don't know if you do that. But this is coming from, this essentially was honored by a Nobel Prize in 68. Sorry, 68 it was developed, 92 was the Nobel Prize. And somewhere there we have Chopper. I don't see, it's probably behind the, yeah, it's probably behind the coats. And for example, this one. There are many others, and you will hear about technology transfer also extremely soon during this week. Now, medical applications, I'm just giving you one slide on this, but you will have a 2 hours lecture by Manjit on Friday, giving you all you want to know about medical applications. CERN is also doing a lot of education, as I told you already. We're training scientists and engineers and technicians, young researchers, physics students, and you, teachers. We have a lot of international audience in our visits. This is protocol visits, meaning visits on the level of at least the minister, not even ambassadors qualify as protocol visits in the year. We have various other activities. There's just a small selection of all the things we are doing until you get to this small white ring here is called LHC, and this is Lake Geneva, and maybe sometime very close to my retirement, so 2030s, we might have a tunnel which is about this size, which is then an accelerator that maybe gets us, or probably would get us, 1 order of magnitude higher. So in contrast to the 14 TeV that we will reach with the LHC, we'll get to about 100. It's a bit bigger, it's quite an engineering challenge, but